Dear students, today we will discuss the law of mass action and the law of chemical equilibrium. Before that, what is meaning of chemical equilibrium we will discuss. Suppose we have a reaction. If suppose A moles of A, B moles of B gives the C moles of C and D moles of D. Okay. For reaction, we can consider if for the stoichiometric, this A, B, C, D is the stoichiometric for the balancing reaction. We consider the total reactant is converted into the product. Total reactant is exhausted or used to obtain the total number of products. Okay, therefore from the 1 mole of A you obtain the 1 mole of B. Therefore total it's consumed to obtain the B. We consider for some reaction it is having possible to obtain the 100% reactant is converted into 100% product. For the stoichiometric consideration we have say that the total reactant is exhausted and we will obtain the product. Okay, that means the reaction is totally completed. Reaction is totally completed means there is not an equilibrium is there. Totally complete. A gives the total gives the product B. We have some examples which is not going to complete. There is some reactant is remains unreactive and some product is the converted, some of them is converted into the product. Okay, suppose we have the example in a closed vessels, okay, that is a glass vessels, there is NO2 plus okay, nitrous oxide, you will obtain the product N2O4. Okay, glass is there, you can monitor that reaction from the by looking the glass. Why? Because NO2 has, okay, both are the same. One NO2 is a dark brown in color and N2O4 is colorless. Okay, as soon as at the start reaction rate is the higher, the NO2 mixed together you obtain N2O4, number of N2O4 molecule is obtained, and number of N2O4 that is colorless molecule is obtained, then the color of this mixture will be get less brown, okay, dark brown to the less brown. But after the long time of reaction, if the faint brown color is remain there. Okay, therefore it means total reactant is not converted into the product. Okay, therefore in first case if 100 molecule is there and 100 is give the 100 product, it means the total reaction is the completed. But in this case if there is 100 NO2 is there, it gives only 90. Okay, for sake of convenience gives the 90 N2O4. But as that is dark, NO2 is the dark brown, as it remains only 10 molecules of NO2. Therefore, the some faint brown color is remain associated with this glass because not total NO2 is completed. From that we can predict that reaction not going to the completion. That reaction there is a equilibrium between NO2 and the N2O4. Okay, therefore, when you observe the 100 molecule is converted into N2O4, that your NO2 molecules remains 10, and your converted is the 90 N2O4 is the converted, your NO2 remains the 10. If this molecule is not reacted and this remains, that product remains constant. If this remains constant, NO2 is remains constant, that is that is the statics equilibrium is there. No change in, no, that molecule is remains as it is, that molecule remains as it is, no change is there. But actually at the molecular level there is some activity is observed. For example, if 10 molecules is there, 100 is NO2, 90 your N2O4 is there. In this case, if there is some conversion is taking place in the molecular from this molecule, if suppose 2 molecule NO2 is converted into N2O4, okay, it opts in the one N2O4. Okay, for the sake of convenience, we have take that example. Okay, that maybe not match. Okay, therefore 2 molecule is converted into 1, and then at the same time its N2O4 one molecule, other N2O4 is decomposes into two N2O4. Okay, like that way there is a equilibrium is established. If 4 molecules give the 2 N2O4, then 2 molecules breaks into the 4 NO2 molecules. There is the equilibrium is like that. If there is a no 10 molecule remains as it is, not use the N2O4 or there is equilibrium. Okay, 10, if 2 is converted, then 1 is breaking into the NO2. But if not like that, if 10 remains as it is, it not breaks. It's not give the N2O4. It's remain as it is. 90 from the 100 molecules you obtain 45. Okay, remember, for the sake of convenience we take the example. It remains as it is. 10 remains as it is. 10. Okay, if suppose there is a one man is living at a home and other is living at the okay, at the other there is a one door is there. If one is remain at it home and one is remain at this home at the long time, then there is no equilibrium. But when it migrate to this side and when this migrate to this side, there is equilibrium is there. Okay, sir, there is the migration is takes the one go to this, there is such migration is there, such, but product remains, its concentration remains same, its concentration reactants remains same, but such molecular level process, NO2 breaks give the NO2 mix give the, but the quantity is not changed. That means that it is at the an equilibrium is established in this reaction. Okay, in this case no color change dark. Okay, if it is reacted, that color total your glass should be the colorless, but it's not converted into totally into O4. Therefore some color you observe and you can predict by observing there is a equilibrium is established, and that is called as the chemical equilibrium. For the understanding, we have also one example is there. That example is H2O, okay, with high temperature. H2 is high temperature, CO, okay, very high temperature, that reaction is going on, and you will obtain the H2 gas and the CO2 gas, okay, at high temperature. Okay, as your reactant, okay, when you draw the concentration versus at the time, at the start H2O, okay, at that point H2O and CO is higher percentage, okay, higher concentration is there. As soon as your molecules collide with each other and gets reacted, okay, they try to react. When they try to react, this quantity gets less and less because it reacts to this, okay, 100 H2O, okay, 10 H2 is there, 10 CO2 is there, okay, at the sometimes 5 reacts and 5 reacts, you will obtain the sum. Okay, therefore its quantity is decreases. As soon as your quantity is the decreases, slowly quantity is decreases. And okay, for H2, for second one, your product at the start was the 0 H2 and CO2. It will also rise, it will goes on rise and at a certain its concentration at the certain times remains the constant. If you heated it or long day you remain as it reaction placed in a vessel, no reaction takes place. There is the concentration of the product and reactant remains there, but it is not a state. If that molecules remain, if that molecules not react to this, not give the equilibrium, if not equilibrium with this, then that is called the static equilibrium, but actually it is not that static equilibrium, it is a dynamic equilibrium. If 100 is there and you convert it into 50, then two molecules react, it gives the 52, and then again the two molecules from this react to this, give the 10 reactant. Okay, such forward reaction and backward reaction is continuously is there, but the concentration of the product is the constant. At the time you increases the time, concentration of the reactant is the constant, because forward reaction, backward reaction, there is continuously, there is a like that changes is takes place at the molecular level. That changes continuously, equilibrium is there, but it not affect the reactant number of reactants and not affect the number of product. That means it obtain the dynamic equilibrium. Static equilibrium is a rigid, there is no change, but in dynamic equilibrium, such kind of at the molecular level, there is equilibrium is established. Okay, like that way, that is called as the chemical equilibrium established in this reaction. And when delta G, okay, at the first lecture we have discussed what delta G is the responsible for whether the reaction is spontaneous or the non-spontaneous. Okay, therefore when delta J get less and less and less, okay, from at the start delta G was higher. Okay, we said that the when G for this reactant is higher, and it tried to lose the G, that is free energy. Remember, it tried to lose free energy, and therefore it tried to lose free energy, and thus you obtain, as the free energy is sufficiently decreases, then equilibrium is established. Therefore sufficiently free energy we have to decreases in the reaction. Okay, that reaction decreases. Okay, therefore like that way there is equilibrium is obtained. Then law of mass action. Okay, one of the given by the Goldbergs and the Peter Wedge scientists, that is what is meaning of law of mass action. If suppose we have a reaction, that is A, B gives the B, that is C moles gives the C, and D moles of the D. You obtain like that. Okay, according to the law of mass action, rate of reaction is proportional to the concentration of reactant raised to appropriate power. That is, that appropriate power is the that is A and B are the appropriate powers we have taken in this equation. Okay, therefore rate according to the law of mass action, rate is a product of concentration. Okay, A is the of the reactant. These are the reactant, product of the concentration of the reactant raised to appropriate power. That appropriate powers in a stoichiometric reaction, in a balanced reaction, A and B is nothing but the number of reactant or the stoichiometric quantity. Okay, we have defined rate of reaction according to mass action is nothing but the product of reactant and raised to a appropriate power, that is the number of reactant. This is our law of action, and when we remove the proportionality constant, then A raised to A and the B raised to constant. If bracket shows that there is a concentration, and that is called as the K is called as the rate constant. Then next we have law of chemical equilibrium. This same reaction is there. A gives the A plus B gives the B moles of B gives the C moles of C plus D moles of D. Okay, therefore by using the law, so there is a equilibrium is there. For this we have studying the chemical equilibrium. Okay, law of chemical equilibrium. First was the law of mass action. Okay, in this case, if you apply the law of mass action for the forward reaction, then it is reactant for forward reaction. Therefore, rate of forward reaction is equal to, you consider if RF is the forward reaction rate, is equal to your K, okay, that is Kf, concentration of A raised to A, concentration of B raised to B for the forward reaction. Rate of backward reaction, is equal to Kr for the backward Kr. Then for backward reaction, this is reactant. Okay? If this moves from this, that will be the reactant for the backward. Therefore, C raised to C and D raised to D. Okay, this is, we have seen that law of mass action previously. Okay, therefore divide equation 2, okay, with the 1. Okay, therefore this equal to this. Okay, for the at the equilibrium, Kf A raised to A, B raised to B is equal to Kr C raised to C and the D raised to D for the case of equilibrium. Therefore, Kf upon Kr is equal to new constant. K constant divided by constant, then the new constant. Therefore, we can say the Kc is equal to C raised to C, D raised to D upon A raised to A and B raised to B. Okay, therefore this is the equilibrium constant. This Kc is called as the equilibrium constant, is nothing but the product of, okay, this C and D means your product of, product means their multiplication. It is product of the your product raised to appropriate power, that is stoichiometric power, divided by the product of reactant. Product means a multiplication. Product of reaction, product of the reactant, concentration of reactant raised to appropriate power, that is the stoichiometric things. Okay, ABCD are the stoichiometric, small ABCD are the stoichiometric, raised to a small ABCD, that is stoichiometric. That is the your equilibrium constant. But for the point study view of thermodynamics, the equilibrium constant, in this case we have to replace this concentration with the activity. Okay, like that way we can activity of C raised to C, activity of D raised to D, activity of A raised to A, activity of B raised to B. Okay, like that we have to replace the concentration with the activity. Now we will discuss what is meaning of the activity. Okay, for a ideal solution mixture, okay, if whether it is a solution or whether it is gas, for the gas the activity is given as, for the solution activity is given, suppose A and B is the so A solution mix the B. Okay, therefore activity for A is given as its concentration upon the standard concentration. Standard concentration is the 1 molar concentration. Okay, that is mole per liter. Okay, that is 1 mole per liter. Okay, how much concentration of A divided by standard concentration, that is 1 molar, that is its value is 1 mole per liter. Okay, this is also concentration of A and its mole per liter. Therefore, this quantity is the unitless quantity. Activity is the unitless quantity. For gases, you can find that the for the gases you can take the pressure of if pressure of that is given by the px and 1 bar. Okay, the pressure, that is the 1 bar. Standard pressure is equal to 1 bar. Okay, that pressure of that component, and if gas is there, is the gas, for the gas we give that equation, pressure of the X component upon the standard pressure 1 bar, that is give the activity for a it describe the activity for the substances. Okay, for activity there is some rules to find out the activity. These are the activities you can find out by this equation, by these formulas you can find out the activity for the ideal solutions, ideal gases. So by using this formula you can find out the activity for elements at the standard state. We consider activity at the standard state for the element is considered as a 1. Okay, therefore in this lecture we have explained number of things regarding chemical equilibrium. I hope you have got all these things. Thank you very much.